All right, let's talk about something really important in the world of piping design. We're going to be decoding a critical piece of the ASME B31.3 code, specifically the part that keeps a solid steel pipe from shattering like glass when it gets cold. If you stick with me, you'll know exactly how to make sure your designs can handle the deep freeze. So let's just start with the question that gets right to the heart of it all. Why on earth would a solid, tough as nails steel pipe just shatter like it was made of glass? I know it sounds crazy, but under the right or, well, the wrong conditions, it is a very real and very dangerous possibility. And this is the exact problem that this whole section of the code is built to prevent. So what's going on here? It's something called brittle fracture. The best way to think about it is with a candy bar. You know, one with caramel in it. At room temperature, you can bend it, it gets all stretchy before it finally breaks. That's what we call ductile. Now imagine you stick that same candy bar in the freezer for an hour. The second you try to bend it, snap. It just breaks, instantly, with no warning. That snap, that's brittle fracture. And at low temperatures, steel can do the exact same thing.
Okay, so how do we stop our expensive steel pipe from acting like a frozen candy bar? Well, the ASME code gives us a roadmap. And honestly, the whole process really comes down to answering one key question. Does my specific material, at this specific temperature and thickness, need to be tested for toughness? So let's look at our first line of defense for answering that.
I know this chart looks a little intense at first, but the idea behind it is actually pretty simple. This is your #1 tool for getting a pass on having to do any testing. You just find your pipe's thickness on the side, go over to the curve for your material, and then drop down to the temperature. If your design's minimum temperature is warmer than what this chart shows, you're probably in the clear.
Not a fan of reading graphs? No problem. The code gives you this table too. It's the exact same information we just saw on the chart, just laid out in neat rows and columns. You just find your material and thickness, and it gives you a precise temperature. It's just two different ways of getting to the very same answer.
And really, that's the bottom line for this first step. If your combination of material thickness and your lowest operating temperature puts you in that safe zone above your materials curve, you're good to go. You are officially exempt from impact testing. And believe me, that just made your life a whole lot easier. But what happens if you're just a little bit below that line?
So what if you're just barely on the wrong side of that exemption line? Does that mean you have to test? Well, not necessarily. The code has a pretty clever trick up its sleeve. See, it knows that a pipe that's under less stress is inherently tougher. So if your pipe isn't being pushed to its limits, the code might just give you a credit that lets you operate at an even colder temperature.
And this chart is how you claim that credit. The logic is so simple. Less stress equals more toughness. So if your pipe is operating way below its maximum allowable stress, this chart here helps you figure out exactly how much colder you can safely go without needing to test. Now, to use that chart, you first have to calculate something called your stress ratio. Think of it like the engine in your car. Let's say the red line is 6,000 RPM, but you're just cruising on the highway at 3,000 RPM. Your stress ratio is 0.5. You're only using half of what the engine can do. It's the same with piping. The lower your stress ratio, the bigger your safety margin, and the code lets you cash in that margin for a lower temperature. Actually, applying this is a really straightforward 3-step process. First, you calculate your stress ratio. Super important. Second, you take that number over to the chart we just looked at, find it on the side, trace it over to the curve, and then down to see the temperature reduction you get. And finally, you just subtract that reduction from the minimum temperature you found on that first chart. And just like that, you've got a new, lower temperature limit.
But look, sometimes even with that fancy stress reduction credit, you still fall short. Your operating temperature is just too darn cold, and you just can't prove you're exempt. When that happens, there's no way around it. You absolutely have to perform impact testing.
Okay, so once you're in the world of testing, the rules can change. A lot, depending on what your pipe is made of. For most common carbon steels, it's pretty simple. If you need to test, you have to test the pipe material and any welds on it. But then you look at something like austenitic stainless steel. That stuff is naturally super tough in the cold, so a lot of the time it's just exempt by default, unless you run into some specific conditions, like having a high carbon content.
The big takeaway here is that you absolutely cannot generalize. The rules for carbon steel are not the same as the rules for stainless steel or for nickel alloys. Every material acts differently in the cold, and the code knows that. So you always, always have to check the specific rules for the material you're using. So, let's say you've gone through all the steps, and there's no doubt about it, testing is mandatory. What does that actually mean?
Well, it means you have to physically prove the material's toughness with a very specific, standardized procedure, the Charpy V-notch impact test. And the code is incredibly direct about this. There's no gray area. This quote right here from paragraph 323.3.1 leaves zero room for interpretation. If testing is required, it's not optional, and it's not something you can do informally. It has to be done exactly according to the rules in the code and the engineering design. The test itself sounds pretty simple, but it's all about precision. You take a small rectangular bar of your material, you cut a little V-shaped notch in it, and then you hit it with a heavy swinging pendulum. A machine then measures exactly how much energy that little piece of metal absorbed before it fractured. The more energy it absorbed, the tougher the material is. All right, so you perform the test. How do you know if you've passed? It's not just about breaking the sample, it's about how much energy it took to do it. And for that, the code gives us very specific acceptance criteria. This table right here, this is your report card. It tells you the minimum passing grade. It specifies exactly how much energy your material sample has to absorb during the test. For a really common carbon steel, for example, the average of your test samples has to soak up at least 13 foot-pounds of energy. If it's anything less than that, the material fails. Simple as that. And that brings us to the magic number 3. You see, the code is all about getting a reliable result, so you can't just test one sample. You have to test a set of 3 specimens, all taken from the same piece of material. It's the average result from those 3 tests that has to meet that minimum value. This just makes sure the result wasn't a fluke and that it really represents the material's toughness. So let's just zoom out and recap the whole journey. It all starts with understanding that brittle fracture is a serious risk. Your first move is always to check the exemption curves and see if you can avoid testing completely. If that doesn't work, you can try that stress reduction trick to get a temperature credit. And if all else fails and you're not exempt, then impact testing with the Charpy test is mandatory. And passing that test means your material meets those minimum energy absorption values. So there you have it. That's the core framework for figuring out low temperature toughness in ASME B31.3. You know the problem, you know the exemptions, and you know the testing requirements. But that leads to one last really important question. The code lists a lot of common materials, but what do you do when you need to use a material that isn't on any of these charts or tables? Well, that's a whole other can of worms and a topic for another day.